This is just a quick reminder that you should feel free to pause the video if you ever feel you want more time to think and write. Welcome to section 5.41, Properties of Logarithmic Functions. So here, I want to show you something. Log of 100 times 10 is the same thing as a log of 1,000. Like I just did the multiplication here and I get 1,000. And if you want to know what is the exponent on 1,000, it's 3. The base is 10, the power is 1,000. What's the exponent? It's going to be 3. On a side note, or compare that to something over here, the log of 100, like you might ask the question, what is the exponent when the base is 10 and the power is 100? Well, the exponent is 2. What is the exponent when the base is 10 and the power is 10? The exponent is 1. And if you add these two together, 2 plus 1 is also equal to 3. Look, we get 3 over here and 3 over here. That must mean that these two things are equal to each other. Interesting. Check this out. Log of base 2. What is the exponent when the base is 2 and the power is 8? Well, the exponent's got to be 3. What is the base what is the exponent? What is the exponent when the base is 2 and that power is 4? Well, the exponent has got to also be equal to 2. And 3 plus 2 is 5. And compare that to this. If you were to multiply the powers, the original powers, 8 and 4, 8 times 4 is 32. And the log of 2, base 2 of 32, like what is the exponent when the base is 2 and the power is 32? It's got to be equal to 5. If the bases are the same, we're starting to see a pattern here. You can multiply the powers and get the same exponent. Check this out. Log base 3 of 9 times 9. Well, 9 times 9 is 81. And what is the exponent when the base is 3 and the power is 81? You'd have to have an exponent of 4. In order, like 3 to the 4th power is 81. And over here, you can compare that to the base of 9 and the base of 9, two base 9s. The powers are 9s. Powers are 9. The base is 3. Base is the same. So you get 3 squared is 9, 3 squared is 9, 2 plus 2 is 4. I'm starting to see a pattern here. It's basically saying that if you've got a log of two numbers that are being multiplied, you can say that's log of the first plus log of the second. Multiplication inside the log, addition outside of the log. That's our first property here. It's called the product rule for logarithms, and you see this log of base a of m times n. That would be m plus log of base m plus log a of base n. The way you can think about it, multiplication on the inside means addition on the outside. So here, if you want to express this as a sum of logarithms, you could say that this is the log of base 3 of 9 times 27. You can split up this multiplication and insert addition here. Multiplication on the inside, addition on the outside. This becomes log base 3 of 9 plus log of base 3, 27. So you're following the instructions here. On a side note, you can take the log of base 3 of 9. Like, what is the exponent when 3 is the base and 9 is the power? The exponent would have to be 2. And here the exponent would have to be 3. 2 plus 3 is 5. Express as a single logarithm. So it's basically going to be the opposite of this. Like we went from a sum of wanting a sum of logarithms to now wanting a single log, and we're going to go in the reverse order. So if you have addition in between two logarithms that have the same base, remember this base, having the same base is absolutely critical. You can't do it otherwise. If you take this addition and turn it into multiplication, this is what you get: p to the third times q. P to the third times q. There's multiplication here inside the logarithm. So let me show you some more patterns. Log of 8 to the 4th. That's going to be log of 8 times 8 times 8 times 8. And then, so basically, if you want to split all this multiplication up, you'd have to write it 4 times. 1, 2, 3, 4. Log of 8 plus log of 8. So the multiplication inside becomes addition outside. But really, we're writing the same thing 4 times. That's kind of repetitive. We might as well just say it's 4 times log of 8, because there's 4 of these. 1, 2, 3, 4. Just like there's 4 of these here. 1, 2, 3, 4. Here, what if there were 5? It would look like this. 8 to the 5th is the same thing as 5 eighths. 8 multiplied by itself 5 times. And then you'd get log 8, log 8. There'd be 5 of these also. And you could just summarize it with 5 times log of 8. Notice, exponent on the inside, multiplication on the outside. Check this out. Log base 2 of 5 to the 3rd. That would be just 5 times itself 3 times. And since it's multiplication on the inside, it becomes addition on the outside. 1, 2, 3 of them. So you can summarize it as 3 times log base 2 of 5. Again, one thing I'm noticing is that here the exponent is 3 on the inside of the logarithmic function, and then on the outside of the logarithmic function it becomes multiplication. Exponent turns into multiplication. Here we got 2 6s, 6 times itself twice, and there's multiplication in between the two, so you can separate that based on the previous rule that we talked about. Multiplication inside becomes addition on the outside. Exponents on the inside become multiplication on the outside. So here, it's pointless to write it out. We found the pattern. We've got 9 on the inside as an exponent, becomes 9 on the outside as multiplication. And you don't have to do the other steps. You can basically say, you can state the power rule like this. Log of base a of m to the p power is the same thing as p times log of base a of m. You can bring the p out front as multiplication. Exponents inside means multiplication outside. So express each as the following as a product. If this is here, if this is going to be log of base a to the 11 of 11 to the negative third, this negative third meant to make this an exponent. It should be an exponent. And then we've got negative 3 times log of base a of 11. The exponent becomes multiplication. Here, the exponent becomes multiplication. We forget exactly what this is. It's the same thing as this. A root here, or a radical symbol, is very related to a fractional exponent. This is 1/4. If it was just a regular square root, it would be 1/2. But it's the 4th root, so it's 7 to the 1/4. If you're taking the log of something like that, the exponent goes out front as multiplication. Here, again, the exponent goes out in front and turns into multiplication. Here we've got log of 1/8. Something else that I wanted to show you. Curious, if you had 1/8, remember that fractions are very related to negative exponents. So these are interchangeable. You can say 1/8 is the same thing as 8 to the negative 1. And now that we've written it as an exponent, you can actually bring this out to the front. An exponent on the inside turns into multiplication on the outside. So this becomes negative 1 times log of base 8. Log of 8. Here, the log of 6/7, the fraction, could be rewritten as 6 times 7 to the negative 1. Again, negative 1 makes it a fraction, puts it on the denominator. But if you bring it up in the numerator, or just as in the same line, you can say this is an exponent of negative 1. Now I see multiplication on the inside, I see exponent on the inside. They become addition and multiplication on the outside. So the log of 6 plus negative 1 log 7. You can you can simplify that down and just say it's log 6 minus log 7. Notice what we had at the beginning, 6 divided by 7. Now it's 6 minus 7. Division on the inside is going to create subtraction on the outside. Same idea here. Log of 4/5, 4 divided by 5. Well, this divided by 5 is the same thing as times 5 to the negative 1. Negative 1 becomes a multiplication symbol, plus negative 1 just turns into subtraction. So log of 4/5 is going to equal to log of 4 minus log of 5. division on the inside, subtraction on the outside. Same thing here. We don't even have to do the intermediate steps. We can just summarize what we see as a rule. It's the quotient rule. And if you have log of base a of m divided by n, it's log of base a of m minus log of base a of n. You make sure you subtract. And like I've been saying, division on the inside is the same thing as subtraction on the outside. So express each of the following in terms of sums and differences of logarithms. Here, you can take log of base z, and I see 3 different variables. 1, 2, 3. What that's going to turn into is these 3 terms. 1, 2, 3. You notice there's multiplication here, so it's addition. There's division here, becomes subtraction. And all the exponents turn into numbers out in front. 2 log zx, 5 log zy, minus 4 log zz. 2, 5, and 4. Now, this normally would be kind of where we end, but I've noticed one other thing. You're taking the log z of z, and that can be simplified too. You might ask yourself, what is log z of z? So I wrote it as an equation. Log z of z would just equal to a, for example. And if we change that to exponential notation, that means that's the exponent, and we want to know what is, when the base is z, what is the power z? Well, a has got to have to be equal to 1 in order for this equation to be true. So if a is 1, then that means log z of z is equal to 1. 4 times 1 is just 4, and that's how you simplify this answer. Let's do the same thing again. We've got log of base z of all this nastiness, and we take a cube root of the whole thing. Cube root is very similar to a fractional exponent, so I'm going to just rewrite it. Instead of the cube roots, I'll write it as an exponent. And then I see right away I can take the 1/3 and put it out in the front. And I'll take a log base z of everything that was inside. There's multiplication and division that corresponds to the addition and subtraction here. And the exponents go out in front. 2 goes out in front of the a. The 5 goes out in front of the c. And this is what we have. If you want to distribute the 1/3 to all of these, which you could have done as a first step, coincidentally, you could have said this is a to the 2/3, b to the 1/3, c to the 5/3. But it comes out here as well. 2/3, 1/3, minus 5/3. That's what the answer is. C, we're going to do the same thing. We've got this nifty little table right here. Just kind of expressing the 3 different rules that we talked about. Inside the log, if you have multiplication, then outside the log is addition. Inside, if it's division, it becomes subtraction. And inside, if it's an exponent, it becomes multiplication. And it goes both ways. Here, we've got this giant messy expression, and we're just going to separate it into 4 different terms for the 4 different variables. 1, 2, 3, 4. This is a right here. Y to the 5th becomes 5 log by. M to the 3rd becomes log b of m with a 3 out in front. And notice that because it's in the denominator, we're subtracting. And I want you to tell me what the last one is. And as an audio check, I might as well let you know, zinc is on the periodic table. It's number 30. It doesn't make it unimportant just because it's all the way down at number 30. I'd like you to begin 5D1 and copy the problem list, do the first problem, and I'll see you in class.